Hi, this is Dr. Gopal Reddy. Our today's topic is electronic spectra of coordination compounds. In that, some selection rules, term symbols, and microstates we are going to discuss. So, come to the selection rule. That means when the UV visible light is incident on coordination compounds, there is a possibility of promotion of electron from its ground state to the excited states. So if the transition need to be occur from the ground state to the excited state, certain rules to it should obey some rules. The rules are called as selection rules. In that, first one is called as Laplace selection rule. In the Laplace selection rule, also called as symmetry forbidden or symmetry allowed transition. That means transition state between state of same parity are forbidden. That Garrett to Garrett transitions is not allowed. Ungarrett to ungarrett transition is not allowed. Garrett to ungarrett is allowed, and ungarrett to garrett is allowed. That means if it is the parity is same, the transition won't be happen. That is called as Laplace selection rule. Second rule is called as spin selection rule. That means transition between the state of different spin multiplicities are forbidden. That means if delta S is not equal to 0, then it is not allowed. If delta S is equal to 0, then only the electron can be changed. Okay, so that is called as spin selection rule. Then if it is come to the term symbol may be defined as the symbolic representation of various electronic states having different resultant angular momentum resulting from spin or orbital or spin orbital interaction, and the transition between two different atomic states may also be represented using their term symbols, which is represented as 2s plus 1 Lj, where 2s plus 1 is called as spin multiplicity, where in that S is called as a resultant spin angular momentum quantum number, whereas L is called as resultant orbital angular momentum quantum number, J is called as resultant total angular momentum quantum number. When the electron is revolving around the nucleus, there will be electron will be exhibit both spin and orbital momentum. So whereas there are three possibilities are there. So one is spin interaction, or orbital interaction, or spin orbital interaction, whereas J is arise due to the spin orbital interaction. Here, first if you consider the orbital coupling, that is L and L. If you consider the any two electrons are present in the any particular orbital, that is given by summation. If the interaction happening between those two electrons, that is orbital coupling, so then that can be represented as resultant total resultant orbital angular momentum quantum number, which can be represented by capital L. So capital L is equal to L1 plus L2. That means if you consider two electrons, L1 is for the orbital angular momentum for one first electron, and L2 is called as orbital angular momentum for the second electron. So that L1 plus L2 is called L1 plus L2, so on L1 minus L2. So these values are lying between those two, L1 plus L2 and L1 minus L2. So example, if you take, so L is equal to 0, that is S orbital. L is equal to 1, it is P orbital. L is equal to 2, that is D. L is equal to 3, it is F. L is equal to 4, it is G. If example in the given example given below, P1 configuration, that means one electron in the p orbital and another electron will be in the another p orbital. So for both p orbitals, L is equal to 1. So L1 is equal to 1 and L2 is also 1. So whereas come to the total angular momentum quantum number, orbital angular momentum quantum number, capital L is equal to L1 plus L2. L1 minus L2, these values lying in that. L1 plus L2 is 2, L1 minus L2 is 0. So that between 1, 2 and 0, there is one more value is lying, that is called as 1. So the total L values are, so 2 comma 1 comma 0. So that if it is L is equal to 0, what I highlighted in the blue one, so L is equal to 2, per 2 the term symbol is D, and 1 it is P, and 0 it is S. Similarly, another example I given, D1 configuration. For D1 configuration, the small l's L1 and L2 are 2 only. So that L is equal to capital resultant orbital angular momentum quantum number, capital L is equal to L1 plus L2 to L1 minus L2. So 2 plus 2 is 4, 2 minus 2 is 0. So 2, 4 to 0, that means 4, 3, 2, 1, 0. So if again come to the L in the blue one, so L is equal to 4, that is G, L is equal to 3, that is F, L is equal to 2, that is D, L is equal to 1, that is P, L is equal to 0, that is S. This is orbital coupling or LL interaction. Then spin coupling, that is SS interaction. If it is come to the SS interaction in the multi-electron system, then the resultant spin angular momentum quantum number can be represented as capital S is equal to S1 plus S2, so on S1 minus S2. That is, S1 and S2 are the individual spin angular momentum quantum number for the electrons, and that can be represented as in the example given below, P1 or D1 configuration. That is, S1 is off and S2 is also off. So that resultant spin angular momentum quantum number capital S is equal to off plus off to off minus off. That is, off plus off is 1, off minus off is 0. So that resultant angular spin angular momentum quantum number is 1 comma Z. So that, so spin multiplicity, that is 2s plus 1 is equal to 3 and 1. Whereas the number of unpaired electrons will be varies the state, that is, if the number of unpaired electrons are 0, then the resultant spin angular momentum quantum number is equal to 0. So that spin multiplicity is equal to 2s plus 1 is equal to, so 1, that is, so S is 0, so 2 into 0 is 0 plus 1 is 1 singlet. If it is unpaired electrons are 1, then the resultant spin will become 2 off, so that multiplicity is 2, so then it is doublet. Similarly, if the unpaired electrons are 2, then it is triplet. If it is unpaired electrons are 3, then it is quadruplet, and unpaired electrons are 5 and quintlet, and so on. Then come to the another final one, that is spin orbit coupling, that is LS interaction. In a multi-electron system, the resultant angular momentum quantum number, momentum L, and the resultant spin angular momentum, that is S, interact with each other, so to give total angular momentum quantum number, which is represented as J, that is J is equal to L plus S minus up to L minus S. So that is given explained in the some few examples down. The state, that is 3s, which will where will be L and S values are given. So per S, term symbol is S, so per S it is L is equal to 0, and for the triplet state given S is equal to 1. So that the J values are L plus S, that is 0 plus S, that is equal to 1. So that the term symbol is given 3s1, that is 1 is called as J value. So whereas 3 is, that is a spin multiplicity, that is 3, and S is term. Similarly 3p they are given. So per P, L is equal to 1. Again, that is triplet is there, the spin multiplicity is 3, so that S is equal to 1. So then J is equal to 1 plus 1 to 1 minus 1. 1 plus 1 is 2, 1 minus 1 is 0. So that the values are lying between 2 and 0 is 1. So that 2, 1, 0. So that term symbols are, so 3p2, 3p1, 3p0. Similarly for D3 also 3d3, 3d2 and 3d1. Then come to the another important topic, that is called as microstate of a configuration. Microstate of a configuration is the state which can represent the energy of the electronic configuration of particular spin, that can be determined by the formula, that is number of microstates is equal to n factorial to the e factorial into h factorial, where n gives the total number of electrons available, that is in the d there will be 10 electrons can be available. If it is p, there are 6 electrons can be available. If it is s, maximum 2 electrons can be available, that is n gives the total number of electrons can be available in the orbital. And E represent the configuration. Example, if it is in the P, it may be P1, P2, P3, P4, P5, P6, what it may be. So E represent the how many number of electrons are available in particular orbital. So H can be number of holes, that is N minus E. So in the below given, the one example I taken, that is P2, all possible combinations of 2 electrons gives 6 factorial, that is P orbital will be having maximum 6 electrons, 6 factorial to the E factorial, that is P2 they are given totally 2 electrons are there, so hence I given E is equal to 2 factorial, and 4, that is n minus E, that is 6 minus 2 is equal to 4, so 4 factorial. If we simplify that, we'll get 15 combination. That mean in P2 configuration, so there can be, we can arrange the totally 15 combination of electron configuration combinations, so that I given in the below, so that will vary with the ml values and ms values, so that is called as microstate. If it is P1 configuration, so the number of microstates can be exist as 6, P2 15, P3 20, and so on. And similarly given with the D configuration, D orbital also, D3 120, D4 210, D5 252, D6 again 210, D7 120, and D8 so 45, so like that. So we can be getting what a different combination of microstates we are getting here. And so before what we have discussed the determination of microstates, that is we can when we get the single kind of orbital, but here we will be having different subshells, that is example P1 and D1 like that. So here microstate that time can be considered n by r into m by s, that is n factorial into this r factorial into n minus r factorial, m factorial divided by s factorial into m minus s factorial, where n is the twice the number of orbitals and r is the number of unpaired electrons in the one subshell, while m is the twice the number of orbitals and s is the number of unpaired electron in the other subshells. So some examples I taken down, that is P1 configuration, n is equal to 6 for both, r is equal to 1, and again m is for another P1, that is can be represented here 6, and s is equal to so 1. So then that to be simplified, that totally will get 36 microstates. Similarly D1 configuration, so for D n is equal to 6 and r1, that is one D1 system is there, so 1 electron is there, so r is equal to 1, and m is equal to 10, and s is equal to 1 for another D, so that will simplify that, so we'll get 100 microstates. So thank you very much.